Yep. Here we go. So do you see my slides now?
Yeah.
My name is Andrea Ferretti, and in the present context, I'm from CNR Nano, Modena, Italy, and here basically I can describe myself as a domain scientist working in electronic structures or running electronic structure simulations, but also active in developing electronic structure codes. I'm mostly involved in the Quantum Espresso project as well as the YAMBO project, that is another code for JW and many body perturbation theory, and I work within the MAX initiatives, that is materials design at the exascale. And I'll try in these 10 minutes to give a brief overview of what we've been doing, because it's also clear. I think there's a lot of similarities between what you are planning to do and what is done here. So about objectives and actions, main point is to enabling the use of frontier HPC systems in the materials domain and with a special focus on electronic structure methods. And so we foresee three main drivers where we can exploit these machines. One surely is increasing size and complexity of the systems we want to study, so put more details in, also meaning larger systems. A second option is to exploit these machines in a high throughput way. Also, these two aspects were nicely highlighted in some of the previous talks, so we resonate pretty well here. And also a third point I'd like to emphasize on is that we can surely increase the accuracy of the our baseline accuracy, so we can use higher end methods. And so if we come to the structure of the MAX project, so what happened here? Basically, here is a list of the work packages. I don't want to be bureaucratic here, but just to highlight what are the main actions that we work on. And here in bold, I've highlighted those that I think that I'd like to cover in this presentation that I think are the most interesting for the present audience. That is the work we do on software architecture, and most importantly, I'd say on performance portability, meaning on heterogeneous machines in particular for the codes we work on. There's also a part on advanced algorithms that are particularly suited for exascale, but I don't have time to cover this. Then a few words about some co-design actions we run, and if we have time, some more information about workflows and data management. Okay, and then there's services, training, and so on, but I think this I'd like to keep apart for the moment. So if you want, then I can outspoke this a bit better. We would like to work on quantum mechanics based codes, getting them ready for pre-exascale and exascale machines. As you know, in Europe, there are going to be 3 pre-exascales machines of the order of few hundred petaflops in 1 year time, more or less. So that is our main goal at the moment, and we need to get ready for exascale machines. One of the key words is to exploit the separation of concerns. So we would like as much as possible to split what is the science and what is the hardware concern. Of course, this is not trivial, and we'd like to integrate these electronic structure codes with high throughput automated workflows. The main tool we use here is AIDA, that has been we use and we developed also partly within the EPFL partner of MAX, and this was already listed in some of our slides. Okay, here is a list of the codes we work on. These are code, we call them the MAX flagship codes. There are Quantum Espresso, Siesta, Fleur, Big DFT, CP2K, YAMBO, and AIDA ecosystem or code automation tool. Here is a list of the partners. Importantly, again, you see these 6 flagship codes. There are basically all the main developers of these codes are on board, and this is pretty important for this kind of activity, plus some supercomputing center, actually the 5 biggest supercomputing centers in Europe, those that are hosting tier 0 machines, plus hardware integrators like ARM and E4 and so on. So now let's come quickly to codes, what has been done about the software architecture. So first of all, codes have been strongly refactored and modularized. This is kind of the practical action to implement some separation of concerns and encapsulation of functionalities. The idea is that we would like to maintain not spaghetti-like code, but an object that is very modular. And ideally, we would like to stop worrying about some parts of the code that are very far from the regions where we are working at the moment. Like if I'm there for a code release, I'd like not to worry about some other parts that haven't been touched in some time. So modularizing is one of the key actions. This takes a lot of time, especially since we are working with some large-scale legacy codes, Quantum Espresso just to name one, but also Siesta and Fleur components that here means libraries and module have been extracted from these codes and made into self-standing objects that are started to be exchanged and also shared, and we'll be very happy to even discuss this with you and share if possible. Also, codes are not frozen or not crystallized here, so these codes are evolving, and new properties and algorithms are invented daily, also for just concern science itself. So we have to keep an eye on the fact that there's an active community of developers there. And if I have to list briefly some of the challenges, one is surely programming models, especially when going to heterogeneity. So what is the best programming models? Most, if not, most of our codes are written in Fortran, modern Fortran, but still Fortran. So we need to come up with something about programming models, especially for GPUs. And then long-term sustainability. We want to be able to maintain these codes. After all, one of the real values of this code is really that there's a lot of community effort that has been encoded in terms of knowledge into these codes, into how things are computed and so on, and we need to preserve this. That gets me to the very last year, this community support and enabling here. I mean, enabling the community to contribute to the code. So we cannot simply disregard this point. So coming to performance portability, one of the, I think, most important actions we have been doing in the past 1.5 years, 2 years, if not more, is really to take these flagship codes to from heterogeneous to heterogeneous machines, so to accelerated machines. And actually, I think that this has been addressed by all codes, and most of them have been already released with some GPU support. And here on the side, you can see a plot. Basically, there's a Quantum Espresso performance on a number of different hardware combinations, all with NVIDIA accelerators here, but also with ARM chip plus NVIDIA. And importantly, basically the compilers were not yet released when those data were produced, so we had access to some preliminary versions of the compilers and so on. So this basically was just possible because of the Max initiative and because of some co-design actions I'll discuss more. And so in terms of accelerators, at the moment we start we target the first NVIDIA accelerators. There's also some work that Anton will be discussing in the next talk, done on AMD cards, and also at Cineca there is some work working within Intel GPUs. And this is somehow summarizes the complexity of this performance portability issue at the moment. That is that we have basically we foresee, and actually these technologies are there already, and there are 3 software stacks, and this has to be addressed since the new machines are going to exploit this hardware. Okay, here is just some data to make everything a bit more real. This is the code I work mostly on, YAMBO, so GW and many-body perturbation theory. And in terms of performance, we've been optimizing MPI, and yeah, so as usually benchmarking, that is, I mean, super important, not as easy to do as we thought first, identifying bottlenecks, solving bottlenecks. So this is the timeline of the evolution. We have a public benchmark repository that was MPI. This is OpenMP, and importantly, in order to run on heterogeneous machines, we're also looking at intranode performance, so looking at speed up obtained using GPUs that for this kind of problem turned out to be pretty good. And here is the whole thing combined. So this is really out of the press data from last week, 2 weeks ago, on Marconi 100. That is a very brand new machine deployed at Cineca. So basically here we were scaling up to 140 nodes with a performance still larger than 50%. This is 4 watts per node, so this is about 1,000 Volta 100 cards. So this is a 8 petaflop single run calculation we were very happy about. And also there's other data I'm not showing here, up to 600 nodes, that is about 20 petaflop single run calculation, still out of this very system. One slide about co-design. This is the kind of activity that is typically dealt with by our colleagues at HPC centers. So somehow this activity puts together technologists, software developers, and engineers from software hardware companies. And this basically has led to some of the data I've shown you before, like interaction with NVIDIA or AMD to have access to preliminary piece of software, compilers, and so on to validate our codes. Also, some co-design vehicles were extracted from Max codes. So on one side, mini apps, but also the whole codes, plus some help coming from the vendors concerning porting and benchmarking. So this is just some advertisement. This is a plenary by NVIDIA CEO at Supercomputing 19, and Quantum Espresso was one of the codes mentioned. So here we were very happy about. Okay, so I think I'm more or less done with my 10 minutes. There's a whole bunch of workflows and data management that undergoes this next part of the talk. So I think I'll spend really 10 seconds saying that all of these codes are basically put together and can work together in workflows by exploiting the AIDA software that is both exploited and further developed within the Max initiative. This, and probably is my last slide, is a very nice image. This is a graph, so each point that are almost invisible is a calculation, and they are connected in a provenance graph. So you start from this relaxation, then you run any a number of other post-processing, and then on top of it you do some more complex workflows. And this is the workflow for computing by Vannier interpolation the bands of 500 materials. So just to give an image concerning the complexity of the workflow you have to deal with. Okay, thanks a lot.